This video, okay, I'll try to make it as short as possible. There's kind of a lot to this. It's about the kinetic theory of gases, and really this is about like, hey, we get like macroscopic things like pressure. Pressure is something you can experience on the macroscopic world. Where does that come from? Well, it comes from the microscopic thing of, little gas molecules bouncing off the sides of things. And then how it all goes together. But essentially, that macroscopic pressure. So if you can imagine, I have, I don't know, this box. It's a cube. Okay, that's kind of a lousy box, but it's a cube. Okay, and inside this you have particles that are bouncing off all different directions. Some are going this way, some are going this way, some are going this way, and everything else. But if we pretend, hey, let's just worry about this one going this way. Well, when it bounces off, it's going to go back this way. And, well, what's happening? And it all bases around this idea. And I'm not going to go through the whole proof, but it starts with, like if this has a momentum of mv, this has a momentum of negative mv because it's going the opposite way. So that my change in momentum is, final minus initial, like negative 2 mv, or just the magnitude would be 2 mv. Change in momentum is F times T equals 2 mv. So you get your force. And you do a bunch more algebra, like, hey, if it's moving, the amount of distance and stuff like that. But eventually what you came up with, okay, again, I'm not going to go through the whole proof. That's what those couple packet pages are for. But eventually you end up with this idea that, that K is equal to 3/2. The kinetic energy equals 3/2 kT. So here's what this is saying. Okay, it is saying the kinetic energy of one molecule depends solely on some constant stuff and the temperature. So and this is really average kinetic energy. Okay, because again, the molecules could be going all different speeds. So the average kinetic energy depends on just the temperature. So you heat something up, it has more kinetic energy. If you cool it down, it has less kinetic energy. But remember, and again, this is for one molecule, which is, this formula is on your formula sheet. You can see it right there. Okay. But remember, this doesn't mean that every gas molecule is moving the same speed. This is the average. And this is why, we did these graphs where it's like, hey, probability, or sometimes they write number of molecules. We'll do number of molecules here, and then the speed down here. So maybe if I have oxygen, and it is at 100 Kelvin, okay? Maybe my graph looks like this, where this was 100 Kelvin, okay? Again, now this is speed. If I wanted to find the speed, we would set this 3/2 kT equal to 1/2 mv squared, because that's kinetic energy. And then you end up with your V equals the square root of 3 kT divided by m. So let's just make sure you guys understand this. This was the root mean square speed. So is it actually the average speed? No, because we're taking the square root of the average, but it's a really easy speed to find, and it's a likely speed. And just a couple things when you're using this formula, because you aren't have to be able to use this formula. T has to be in Kelvin, and m is the mass of one molecule. One molecule. For example, if I was taking O2, okay, O2 has a molar mass of 32. And what does that mean? That means grams per mole. So if you wanted to figure out, okay, the mass of one molecule, you got to do some, like this stuff, where it's like, all right, so I got 32 grams per mole. And here's what I want. Can you see if I write over here? Yep. I want my eventual thing needs to equal kilograms per molecule. Okay? Well, so then what do? All right. So if I want to get to kilograms, I need to get rid of grams. So I'm going to do 1,000 grams over 1 kilogram. All right, so now I would have a kilogram per mole. Oh, shoot. So then I want kilogram per molecule. So I need to get rid of my mole. So I have 1 mole, and I would have, this would be 6.02 Avogadro's number times 10 to the 23rd. And then if you did that, you would get a really small number, but that makes sense because we're finding the mass of 1 molecule. Just that's it, okay? So as far as like doing it, I think if you guys write it out like this, it's not too bad. Okay, so like write it out, take the time and practice it. But anyway, going back to our thing, so let's say we do this and you get, hey, really what this is saying, this here is saying, is that if this was, I'm going to make up a number, I don't actually know what it is for oxygen, I probably should have done that ahead of time, but we'll make up a number and say that this is, I don't know, 400 meters per second, okay? So if this right here is 400 meters per second, I know you can't really read it, but take my word for it, it says 400. Then the RMS speed would probably be like right around here. So maybe that's 420 meters per second. Well, does that mean every molecule is going 420 meters per second? No, of course not. Average. There's going to be some that are going really fast, some that are going really slow, okay? But if this was 100 degrees, if I wanted to show you what it would look like, for example, let's say 200 degrees. Well, 200 degrees more, so that means it's going to be going, a graph's going to look something like this. If this is still number of molecules of the same gas, that means the area underneath has to be the same. If it's probability, the area wouldn't have to be the same. So just be careful with the, like your axes. Number of molecules, well, it's the same number of molecules, so the area has to be the same. If it's probability, well, it wouldn't have to be the same. But that gets shifted over more. If it was something that was colder, so this would be like 200 Kelvin. If it was something that was colder, like 50 Kelvin, then it would look something more like this. Okay, but again, that area probably have to be a little bit bigger. But that area would have to be the same. Hang on. I lost my screen. All right, I'm still going. Okay. Does that make sense? So like this would be 50 Kelvin. Speed's less. And then we use this later on in the unit that this was the average kinetic energy for 1 molecule. So if I want to find then what is the, what is the stored energy of all the gas? What's the internal energy of the gas? Well, why does gas have energy? Because those molecules are moving around, okay? So then really all I have to do is just take this, if I want the energy for the internal energy for the whole gas, well, I just have to take this and multiply it by the number of molecules that I have. So it would be this over this times the number of molecules times KT. So there you go. Hopefully that helps. Bucky!